In this video, we are going to focus now on double integrals over more general regions, looking at evaluating them, setting them up, the differences compared to integrating over a rectangular region, all pieces that we will cover in this video. So starting out with evaluate the double integral of 2x cosine of y squared dx dy. So we have our order of integration, dx and then dy. The inner bounds of integration, as a reminder, are the x bounds. The outer bounds are the y bounds. So x goes from 0 to the square root of y goes from 0 to the square root of pi over 2. First thing to notice right away in this video is there is now a variable expression in one of the bounds of integration. And that's the biggest change we are going to see when we are integrating over a more general region, not a rectangular region. The bounds are no longer constants. So, integrating with respect to x gives us integral of 2x. So we have the integral of 0 to square root of pi over 2 of x squared cosine of y squared from 0 to the square root of y dy. And again, just in this first example, that reminder that these bounds are being plugged in to the x variable. So integral from 0 to the square root of pi over 2 of square root of y squared is y, cosine of y squared, minus 0, so no second term there, dy. Now we're going to integrate with respect to y. So we would underline y squared. If we were doing a formal u substitution, that would be our u. U would be equal to y squared. The derivative with respect to y is 2y. So I need a 2. Means we need to divide by 2. That 2y we circle, that would be our du in a formal u substitution. And we're integrating cosine of u. We're thinking about this as the integral of cosine of u, which will be equal to that 1/2. So 1/2 integral of cosine is sine, and y squared is that u term, so just of y squared. Evaluate that from 0 to the square root of pi over 2. Not as significant here, but just a reminder, these are now the y bounds that we are plugging in for y. So we have 1/2. And I'll factor out the 1/2. So then we have sine of square root of pi over 2 squared. So that's just sine of pi over 2. Minus sine of 0. So that's going to give us 1/2 times 1 minus 0, which is 1/2. So the steps for integrating, those stay the same. All that changes when we're integrating over a more general region is that inner bound of integration is going to have a constant. Now, another thing does change, and it's important to talk about, especially in this problem. If we look at this function, some of you may have recognized that this function could have been separated as 2x times cosine of y squared, which over a rectangular region, we treated as a separable double integral, and we separated it into two single integrals. Over more general regions, so once variables start to become incorporated in the inner bounds of integration, we no longer can separate double integrals, right? So nothing in this video will be separable because the inner bounds of integration are going to have the variable that we have yet to integrate with respect to. Okay, so important to note because oftentimes we learn separable double integrals with rectangular regions and want to extend that idea, but it does not extend to more general regions. Another evaluate the double integral of y squared divided by x to the fourth plus 1 dy dx. So again, inner bounds are the y bounds, outer bounds are the x bounds. So now being the second problem, another thing to notice is the variable we use in the inner bound is always the variable we are not integrating with respect to. So phrased a little differently, we are integrating with respect to y first, right, inside out. We should only have x's in the inner bound of integration. And then the outer bound should only be constant, and that's something we'll address in a few slides. Okay, so integrating with respect to y, we have the integral from 0 to 2 of 1/3 y to the third over x to the fourth plus 1. Evaluate that from 0 to x dx. And again, these are y values that we are inputting in. So 0 to 2 of, we can put the 1/3 in front. This is just a good reminder that factoring out a constant from an integral, be it a single or a double integral, works. Right? So we can take the 1/3 in front, and then we'd have x to the third over x to the fourth plus 1. And then if we plug in 0, so minus 0, so there would be no second term again here, dx. Not always the case, just these two first examples that wound up being true. Now we need to integrate x cubed over x to the fourth plus 1. So underline x to the fourth plus 1, that's our u in a formal u substitution. The derivative would be 4x cubed, so a 4. And then we need a 1/4 to adjust. Circle the 4x cubed, that would be our du in a formal u substitution. And that means that we are looking at a natural log integral. So we have 1/3 times 1/4, so 1/12, natural log of the absolute value of x to the fourth plus 1. And we're going to evaluate that from 0 to 2, which again, less significant here, but equally as important. These are x values we are plugging in. So we get 1/12, and I'll leave that factored out. So natural log of 2 to the fourth, so that's 16, plus 1, natural log of 17, minus the natural log of 1. And the natural log of 1, if we remember, is 0. So this is just equal to 1/12 natural log of 17. So we've evaluated two double integrals now over general regions, one dy dx, the other dx dy. Okay, so we've seen the order, right, can be done either dx dy or dy dx for these double integrals over general regions. Now, speaking on order, if we're giving a more general problem, how do we decide whether we should be integrating over a region as dy dx or dx dy? And that's the next focus in the video. So there are two types of regions that we are going to define for these double integrals. So a region R in the xy plane is of type 1 if it lies between two continuous functions of x, g sub 1 of x and g sub 2 of x. Okay, a picture here is going to help significantly so you can get a better sense of what a type 1 region is defined as. So we're going to draw two different ones so we can see. So let's just x, y, we'll label our axes. Okay, so we're going to go from a to b on the x. And then I'm going to draw two continuous functions in terms of x. So let's say we have this, we'll call this y equals g sub 1 of x, and we have that, which is y equals g sub 2 of x. And these curves can go on, but we're only focused on looking at them from A to B. So there's our region. So we consider this to be a type 1 region because we can draw vertical lines through this region that always start on g sub 1 of x, so a function in terms of x, and they end at the top on a different function in terms of x, which is g sub 2 of x. And we go along the x interval from A to B. Often we refer to a type 1 region as vertically simple. We can draw these vertical lines. They would define the bounds of integration to functions of x, and then we're going to go from A to B with those vertical lines. Another example of a type 1 region, so A to B still. So now let's draw it so that those functions intersect. So y equals g sub 1 of x and y equals g sub 2 of x. So now they intersect conveniently at a and b, but same thing happens if we draw vertical lines through the region. We always start at the bottom on g sub 1 of x and end up top at g sub 2 of x. Okay, two different functions in terms of x. So these are two examples of a type 1 region. There are so many, we wouldn't be able to cover all of them, but the idea is these are vertically simple regions. We can draw these vertical lines cleanly. They always start at the same function, end at the same function from bottom to top. Okay, and we can even make a note of that, right? Here we're really working bottom to top. And that'll be important for setting the bounds of integration as well. So formally, the region can be defined as region R, which is all points xy, such that x is in between a and b inclusive, and y is bound between g sub 1 of x and g sub 2 of x inclusive. And if this is how we can define the region, then the double integral, which is really where our focus is in this video, can be set up. So double integral f of xy. So first thing, order. When we're talking about a type 1 region, since y is bound by two functions of x, we need to integrate with respect to y first. So dy and then dx. Okay, so anytime that we draw those vertical lines in our region, order is going to be dy dx. The y bounds, g sub 1 of x, g sub 2 of x. So those are the functions of x. So integrating with respect to y, the bounds are in terms of x's, and then x goes from a to b. So that's what our double integral setup would look like over a type 1 region. So if there's a type 1 region, that means there's a type 2 region. So a region R in the xy plane is of type 2 if it lies between two continuous functions of y, h sub 1 of y and h sub 2 of y. So we'll draw two examples of a type 2, although there are plenty. So we're going to go from C to D now on the y-axis, and our functions are going to be in terms of y. I had to pause there for a second. Okay, so now let's say we have a graph that looks like this and a graph that looks like that. So this would be x equals h sub 1 of y, and this is x equals h sub 2 of y. Okay, we're capping the region from C to D, right? So that would close the region off. So there's our region that we're integrating over. So now instead of drawing vertical lines through the region, we can draw horizontal lines that go from left to right. And we know this is a type 2 region because we always start on the same function on the left and end on the same function on the right. And we're able to do that throughout the whole region, hence a type 2. Another example of a type 2 region, let's draw a region where the curves intersect. So let's say like this and like that. So on the left we have x equals h sub 1 of y. And on the right we have x equals h sub 2 of y. Again, we're able to draw these horizontal lines now through the region, going up, starting at C, all the way to D. Okay, so for a type 2 region, our thought process is left to right, which again is helpful when we're setting up the bounds of integration. So the region can be formally defined now as the R being the set of all points xy, such that y is bounded between C and D, and x is bounded between h sub 1 of y and h sub 2 of y. So now x is in between two functions of y, and then y is going between two constants, C and D. And what we care about, setting up a double integral over a type 2 region, we'd have the double integral of the function f of xy So now, since x is bound between functions of y, we need to integrate with respect to x first. And also visually, we see it. That's the nice part about drawing those lines in, those horizontal lines. Because we're working left to right, we're working along the x-axis first, and then we're moving up the y-axis with each subsequent horizontal line that we draw. Right? So there is a reason, so then dy, to draw out the region and to draw those lines in. X goes from h sub 1 of y to h sub 2 of y, and then y goes from c to d. Right, so notice we've spent some time here talking about both type 1 and type 2 regions because they are so important. The integration is really second. That's a skill that we're going to practice throughout this unit anyway, but being able to identify and set up our double integrals over type 1 and type 2 regions is really the most important skill we need to come away from with this video. Okay. And I think I switched it. Come away with from this video. That makes more sense. All right, so since double integrals represent net volume, evaluating should always have a constant answer. Essentially, that means we should always get a number. Hey, we should never evaluate a double integral and wind up with something that has a variable in it. If we did, something went wrong. And most likely what it means is the outer bounds, because the outer bounds of integration should never have variables in them. And this is a really important idea, regardless of double, triple, any level of iterated integrals. The outermost bound should always have constants. Okay, and that's what's going to lead to having a constant answer after we evaluate, okay, whatever the integral is representing. So, important idea, make sure as we go and set up integrals that our outer bound is always constants. It is possible to change the order of integration, but unlike rectangular regions, the bounds of integration cannot be just be switched. This little line here is its own video in and of itself, and that will be in a few videos from now. Changing the order of integration over a more general region can be done, right? Fubini's theorem does work, but it requires more work and more attention to detail. For rectangular regions, we really had the flexibility to just change the order. If we didn't like dy dx, then just go dx dy and change the bounds pretty easily. Right? But we'll explore this line here in a video of its own. So let's practice setting up. So set up an iterated integral of the function f of xy over the given region R for both orders of integration. Okay, so here we have our region. Let me move up here. Okay, so we have y equals x squared and y equals the square root of x as the two curves that are bounding the region R. So that's R. And actually, I don't want to draw anything inside of it. Okay, so let's first treat this as a type 1 region. Okay. First thing we need to decide is where they intersect. And we can kind of estimate that, but it's not always going to be that easy. We're going to need some algebra at times. So just to show you what that would look like, we would want to set both functions equal to each other. Then we're going to square both sides here. Right, go through the process of some algebra. So x to the fourth equals x to the fourth minus x equals 0, x times x cubed minus 1 equals 0. So either x equals 0 or x equals 1. So I forgot, there's that other point of intersection. So we have 0 and we have 1. And if we need the y, if x is 1, y is also 1. Okay, so that's always first thing. We might need to find the intersection of the curves. So now as a type 1 region, we want to think vertically. So we want to draw vertical lines through the region. And that's going to help us determine what the bounds of integration should be. So we have the double integral of the function f of xy dy dx. We're thinking vertically first, which is dy, and then we're going to move left to right. So on the lower part of each vertical line is the function x squared, so that's our lower bound of integration. Then the top of each line is bound by the square root of x, so that's the upper bound of integration. And then on the x-axis, right, this is our x, this is our y, we're going from 0 to 1. So there is our setup of the double integral over a type 1 region. Now as a type 2 region, so type 2 region, we're going to think left to right. So left to right here, which does mean we need these curves in terms of y instead of x. So if y equals the square root of x, that means y squared equals x, or x equals y squared. And if y equals x squared, that means square root of y equals x. Okay. So those define the left and right curves, and then we're going to go along the y-axis. So we have the double integral here of the function f of x, y. Now we're going dx, dy. So on the left, we're bound by x equals y squared, so our lower bound is y squared. Then on the right, we're bound by x equals the square root of y, so square root of y is the upper bound. And then on the y-axis, we're going from 0 to 1. So notice it doesn't really matter if the curves intersect or if it's a vertical or horizontal line that ends the region. Really, once we get to the outer bounds of integration, we're looking at what is covered on either the y or the x-axis. In this case, we cover from 0 to 1 with those horizontal lines that we drew. Okay, let's look at another example that brings in a new idea. So if the region R can be expressed as the union of two smaller regions, so R can be expressed as R1 union R2, where R1 and R2 do not overlap except at their boundaries, then we can express the double integral over the region R of the function dA in another way. So just pausing for a second, what this means is essentially instead of treating the region R as one big region, we might have to break it down into smaller regions, the sum of smaller regions. And this could be for any number of reasons, but often it's because either the bottom or the top or left or right, depending on which type we're looking at, changes, right? And we'll have an example to really show what this means. So if we can write R as the sum of two smaller regions, then we can write the integral as the sum of two integrals. So we can say that this is the double integral over R1 of the function plus the double integral over R2 of the function. Okay, so region can be expressed as the sum or the union of two smaller regions. Then we can break up the double integral as a sum. So set up an iterated integral of the function f of xy over the region R, bounded by the lines y equals x plus 3, y equals 3 minus x, and y equals 0 for both orders of integration. Okay, so first let's do a little drawing of our region. Okay, so y equals x plus 3. That looks like that. Y equals x plus 3. Y equals 3 minus x. Y equals 3 minus x. And then y equals 0. Y equals 0. Okay, so we want to treat this as both a type 1 and a type 2 region. Okay, so type 1, we're thinking vertically. So we draw, let's go red. We draw vertical lines through the region. And this is where we run into an issue. So type 1. The function on top changes. So on the left half, x plus 3 is the function that we hit on top. But then on the right half, we hit 3 minus x. So we need to split into two separate double integrals to address that fact. So here we have the double integral of the function. Type 1, we're thinking vertically, so dy dx. So on the left half, our vertical lines go from 0 to x plus 3. and we're moving along the x-axis from -3 to 0. And then plus, take the double integral. On the right half, we're going, let's finish, f of xy, still dy dx. So we're going from 0 to 3 minus x now. And on the x-axis, we're going from 0 to 3. So we might have regions that we have to split. Or, if we look at this region horizontally, notice there are no issues. So x here would be y minus 3, and x would be 3 minus y. So as a type 2 region, we only need one double integral. So double integral of the function f of x, y. We're thinking horizontally, so dx, dy. So on the left, we're going from y minus 3 to, on the right, 3 minus y. And then on the y-axis, we're going from 0 to 3. So that's another important reason to be able to identify regions as both type 1 or type 2, because there are instances, we could do both here, but type 2 sets us up for a much easier problem, because we're only doing one double integral as opposed to two. So let's put this into action for two problems to finish out the video. So evaluate the double integral of e to the y squared, where r is the triangular region with vertices 0, 0, 0, 1, and 1, 1. Okay, so we have our little region here to draw. So 0, 0, there's 1, 1. So our region, so 0, 0, 0, 1, 1, 1. So there is our triangular region. So this is the line y equals x, which makes life easy. We have y equals 1 and x equals 0. So we're going to evaluate the double integral of e to the y squared. So this can be done either way, type 1 or type 2. We could draw vertical or horizontal lines just as easily in this region. But look at the function, and this is important to pick up on. This function would be very difficult to integrate in terms of y. We would try to underline 2y, there is no y, and we would be stuck pretty quickly. So for that reason, let's choose our order to be dx, dy, which means in our region, we're going to draw horizontal lines going across. We're treating this as a type 2, and we can even write this. We're going to treat this as a type 2 region, not because of the region, but because of the function. Right? So there is that balance of looking at the region, but also looking at what we're trying to integrate. So we're going to go from 0 to y, and then on the y-axis go from 0 to 1. So integrating with respect to x works out pretty nicely. So 0 to 1, x e to the y squared, from 0 to y dy. So remember, these are x values. So we have the integral from 0 to 1 of y e to the y squared minus 0 dy. So now integrating, underline y squared, that would be our u in a traditional u sub. So then 2y over 2, du is 2y. So our integral is 1/2 e to the y squared. Evaluate that from 0 to 1. So we have 1/2 times e to the first minus e to the 0, which is 1. So 1/2 times e minus 1. Right? So this problem really puts everything together. Identifying the region, picking type 1 or type 2, setting up our double integral, and then integrating. Okay, one last example. Evaluate the double integral of x, y, dA, where r is the region bounded by the parabolas y equals x squared, y equals 2 minus x squared, and the line x equals 0. Okay, so y equals x squared will look like this. Y equals x squared. 2 minus x squared will look like that. And x equals 0 right there. So we have x, y. So region looks to be type 1 more easily than it would be type 2. we do need to find this point of intersection. So we have some algebra to do. So x squared equals 2 minus x squared. 2x squared equals 2. X squared equals 1. X equals plus or minus 1. So for this region, that point of intersection is positive 1. Okay, so now we get to work. So double integral of xy. We're going dy dx since it's a type 1 region. Y goes from on the bottom x squared, on the top 2 minus x squared, and then we're going from 0 to 1. So we integrate. So integral from 0 to 1 of 1/2 x, not x squared, y squared. Y squared evaluated from x squared to 2 minus x squared dx. So we have the integral from 0 to 1. We can take the 1/2 out. So then we have x times 2 minus x squared squared minus x times x to the 4th, so x to the 5th dx. Now we integrate this first term, so we would underline 2 minus x squared, that would be our u. du would be negative 2x, so negative 2 over negative 2. Circle the negative 2x, that would be our du. So we have 1/2, negative 1/2, 2 minus x squared to the 3rd times 1/3. And then minus 1/6 x to the 6th. And we're going to evaluate that from 0 to 1. Okay, so we have 1/2 and then negative 1/6. Plug in 1. 2 minus 1 is 1. 1 to the 3rd. I'll write that out just so we have it. 1 to the 3rd. Minus 1 to the 6th times 1 to the 6th, minus, well, plus 1 over 6 if we plug in 0, 2 to the 3rd, and then minus a negative plus 0, which we can write for emphasis there. So we have 1/2 times negative 1 over 6 minus 1 over 6 plus 8 over 6, which is 4 over 3. So we have 1/2. So that's negative 2 over 6, so negative 1 over 3. Negative 1 over 3 plus 4 over 3, which is 3 over 3, which gives us an answer of 1/2. Okay, so 3 different parts of this video: evaluating double integrals over general regions that were already set up for us, then discussing type 1 and type 2 regions, and then using those to build our own double integral and evaluate. Practice is going to be key as always, really in identifying those type 1 versus those type 2 regions and deciding which is the best way to go.